they do is they talk about trajectories and fastballs going hoops.
Do you really think that me and my husband talk about math all the time?
Yes.
Case already knows how to take derivatives, so.
See, it backwards up is surprising. Like, should kid.
No.
It already is getting college level classes.
All right. Here is the fundamental theorem of calculus. Please write it down.
This one, the second one.
Sorry, the second fundamental theorem of calculus. You have the derivative with respect to x of the integral from a constant to x of f of t dt. And it equals f of x. Anybody? Okay, what I'd like you to do within your pods, talk about maybe why this would make sense.
Hey, Miss Holman. Guess what we're doing in business today? An egg drop. Right above your plate. We do two names. I'm gonna do it.
All right, let's discuss as a class. Does anybody have a nice way of explaining why this is legitimate?
Because you told us so.
Not a good reason. What does this mean?
Derivative.
Take the derivative. What is this? Okay. So what do you think happens when we take the derivative of an antiderivative? You get back to where you started, your function x. Okay. Right, but you're going from a constant to x.
But you just said the derivative and the derivative cancel out, so you don't worry about that. So why is it?
Right, but when you evaluate this, okay, let's go through this.
Stand up, stand up, stand up.
Ready.
When you take the antiderivative, right,
What was the statement about the doctor?
we get f of x minus f of a, right? Well, if a is a constant, then f of a is just going to be a constant, right? So when you take the derivative of an antiderivative, you go back to f of x, right? When you take the derivative of a constant, you get 0.
So what is the t supposed to stand for? Just a random.
Well, you can't have x as a limit of integration if you have f of x dx. That doesn't make any sense. And so whatever's inside your antiderivative is going to be a different variable. Whatever's inside your antiderivative is going to be a different variable, but as long as x is in your limit of integration, then that's how those are connected. Well, it's whatever's inside.
So the f of t and the f of x is the same.
It's the same function. It's the same function, yes.
Okay, so if it's like x squared.
Let's do an example. How would that sound?
That would be wonderful.
Let's go ahead and do this.
Okay.
The derivative with respect to x from the integral from 3 to x of t squared plus 1 dt. It does not matter what your lower limit of integration is, as is a constant. Okay, so if I take the derivative of this antiderivative, what are we left with? X cubed plus 1. Done.
That's it.
Oh, you have to plug in the X.
You don't have to show any work. It's done. Yeah.
That's it.
Yeah. Don't you?
Wait,
There's no catch.
Like the course is like
The derivative of an antiderivative is back to the original.
some surprises lurking.
Some surprise is lurking. We will see. Okay? So, Nolan. Beautiful. You redeemed yourself. Okay. Okay, so I agree with sine x to the 6th. However, what happens when we take the derivative of a function inside of a function? Chain rule. Which means we have to perform the chain rule with that x cubed. So there's going to be a 3x squared sine of x to the 6th. Because the derivative of x cubed is 3x squared. When you have a function inside of a function, you have to perform the chain rule. Well, we're taking the derivative of an antiderivative. And inside of our antiderivative is x cubed. What, Katie? Okay, so listen to that. Oh, okay, I see where you would get that. But our inside function is x cubed, because that is what is in our integral. Right, because the derivative is going with that guy.
Yeah.
Okay, let's do another one. Now, make sure our lower limit of integration is a constant. Our upper limit of integration is x cubed, which means we're going to have to use the chain rule. Well, if it's not like, if you have the, like if you had this, later internet somewhere. Because you do have something like this in your homework. If you have something like this, you would actually have to preform the integration and then take the derivative. Because both limits of integration have to do with x. So you would perform the integration, you would integrate that to 1/2 t squared and do the first fundamental theorem of calculus, plug in x plus 2 minus plug in x, and then work back. Okay? Okay, so do you want to do this example that I made up off the top of my head real quick?
Yes, yes, I do.
Sorry.
That's okay. You know what? Let's go ahead and finish the one that's on this slide, and then I'll do one like that, okay? So let's go ahead and do the one on the slide. Our lower and ooh, wait on that. Okay, so we have the square root of what? X x cubed cubed, right? Because we're going to plug x cubed in for t cubed. So we get x to the ninth. Okay. Power to a power, you multiply, and then using the chain rule, what goes out in
3x
front?
squared.
Okay. So if I had one like this, the derivative with respect to x of the integral I'm going to make this nicer for us. I'm going to make it 2TDT. Because what happens when we integrate? You just get t squared, right? Evaluated from x to x plus 2. Now, if one of those was a constant, okay, we know the derivative of a constant goes away, which is why we can use the shortcut we've been using, like I showed you on that first slide. However, when we plug this in, we get x plus 2, the quantity squared, plus minus x squared, fundamental theorem of calculus number 1, right?
And then you evaluate that.
Now we can take the derivative.
Now you can do it. So that's your answer.
Well, 2x plus 4.
Wait, why did...
Well, I
Wait, 2x plus 4. Wouldn't that be just 4?
Yep. I had that as a 2x on my head, I apologize. So 2x minus 2x is now 0, then plus 4. Okay? I want the derivative of f of x. I did. You were right. Okay. So, what do you think? The derivative. Okay, so x cubed goes inside of cosine, and 3x squared goes into the number. Not multiplied out. Yep, okay. Thank you. Great vocabulary. All right, now, what if I ask you for this? Negative 3x squared cosine of x cubed. Because the limits of integration are switched. Okay?
Is that what we didn't do for the ones that was like like if we get one where there's a constant on top and there's the x on the bottom, we just flip them.
Yep. And just make it negative. Yep. Yep. Okay. accumulation function. Why would it be called an accumulation function? Here I have the graph of f, and g is the integral of f. Why is it an accumulation function? What are we adding up? What are we adding up? Area. When we integrate, we're adding up area under the curve, aren't we? Okay. So if I am asked for g of 1, g of 1 is the same thing as the integral of 0 to 1 of f of t, right? Well, if this is f, how do I find the integral from 0 to 1 of f? Yeah, it's this right here, isn't it? Oh, what is that? How do you find the integral area? And what's our base? And our height? So 3 halves. That's how we get the accumulation function. That's what it's called, accumulation. Okay. Now, g prime of 1. What is g prime? Which in this case is what? Yes. The derivative of g would be the derivative of the integral, which is f of x. So if I ask you for g prime of 1 on that graph, what are we looking for? The function value at 1, which is 0. If I asked you about the second derivative of g, the second derivative of g is the same as the first derivative of f, which is, what is the slope? So the slope is -3. G of 1, since g is defined as the integral, we're talking about the area. Okay. Now, I want to know where g is increasing and decreasing. What graph do we have of g? We have the derivative graph. So, if this is the graph of the derivative, if I'm talking about increasing, let's think back to chapter, whatever that was, 3. Negative 1 to 1 because our derivative is positive. Right? When we talk about decreasing, we want to know where our derivative is negative. Negative what? Negative 2 to negative 1. I would like to let you know that our internet has been unbelievably slow yesterday and today, and so that's why I'm getting all these jumps, because the connection is just awful. Okay, concavity. If I'm looking at the derivative graph, then how do we know where we have concave up? Where our first derivative is increasing. So where's the first derivative increasing? Negative 2 to 0. So we're concave up from negative 2 to 0, and we're concave down from 0 to 2. Okay? We are going to tie some graphical analysis back into this fundamental, the second fundamental geometry. Okay? Like that? All right. Now, I kind of want to reminisce about the first fundamental theorem of calculus. Let's say that we know our derivative is 4x. We know our derivative is 4x. And we know our function value at 0 is 6. How can we find a different function value? Okay? We can do this one of two ways, and I'm going to show you both ways. Okay? This is what's on your worksheet that I'm supplementing your homework with. Okay? So, the first way okay. So, if I have the derivative, how do I get the function? We integrate. Okay. Well, when we integrate 4x dx, what do we get? We get 2x squared AD plus c. Okay? So we just took the integral of our derivative. So that means f of x is 2x squared plus c. Well, how the heck do I know what c is? Can we find c? We know our function value at 0 is 6. So that means our function value is 6 when x is 0. Which means our f of x is 2x squared plus 6. Can we find f of 3?
Yeah.
What's f of 3?
4.
That is way number 1. Now, I said we were jumping back to the fundamental theorem of calculus. This had nothing to do with the fundamental theorem of calculus. No. Let's talk about the fundamental theorem of calculus, okay? We know f of 0. We want f of 3, okay? So, we can integrate from 0 to 3 of 4x dx, and what must that equal? F of b minus f of a. F of 3 minus f of 0, right? If this is our derivative, right? Okay, this is our derivative, and so it should equal the function evaluated at b minus the function evaluated at a, right? Cool. All right, so we have 2x squared evaluated from 0 to 3, and that should equal, what was f of 0? Okay. Ooh. Minus 6. I apologize. So 2x squared from 0 to 3. We have 18 minus 0 equals f of 3 minus 6. Wow, crazy. We got the same thing. So you're saying we graph f of x, and from 0, this is the derivative graph, because that's what we know, right? Are you talking about finding the area under the curve? Which is the same thing as what I'm doing here, right? Yeah. But it's not always going to be a line. Okay. So it's not always going to be like that. Okay? So you have one of two options. You can find C and write your function and then plug the value back in. Or you can use the fundamental theorem of calculus. It's quicker. How would you screw this up? Doesn't matter. It doesn't matter. I prefer the fundamental theorem of calculus. I think it's quicker anyway. I feel like this is a lot more work, this first way. It doesn't matter. Okay? The AP graders will accept either way. Now, something you need to be careful of is notation. Once you take the integral, stop writing the integral sign and the dx. Make sure when you write an integral, there is a dx there. Okay? They will be picky about notation. Okay? When you're taking limits, write the limit until you take the limit, and then you don't have to write the limit anymore. Okay? Now, on this differentials worksheet, the first few problems are just going to ask you, hey, this is the derivative, and here is the value of the function. Find the function. So that is just what we did here, but stopping after we find C. Okay. So the first 4 problems you're going to have to do, you're going to have to find C, basically, to find your function. Okay? And then the last 3 problems on the worksheet are finding an actual value.
One question, I was supposed to be A1 and this wouldn't make sense if you're A1 is bigger than equals.
Yep. I'm going to make it.